All right, here we go. Thank you. You're welcome. All right.
All right, welcome to our Math 106 exam for week session. We're gonna just take whatever questions you have, and I have some prepared problems. If you would like any of the prepared problems, they can be dropped in the chat. So I'm just gonna go ahead and start going through some of these practice problems. At any point, please feel free to ask questions or drop questions in the chats, or ask your own separate questions. So we're going to look at this first one. It says this is a picture representing the famous Königsberg Bridge problem, which is a famous graph theory problem. It asks us to draw a graph and then use it to determine whether it is possible to travel each bridge exactly once. So the first thing we're going to do here is we're just going to go ahead and draw our graph. So on these problems where you have land masses and bridges, our land masses are going to be our vertices or our points, and then our bridges will be our edges. So you want to look first at how many land masses do I have? And I can see on this picture, I've got like this north shore, this south shore, and then I've got 2 islands as well. So that's a total of 4 land masses. So that means that when I draw my graph, I'm going to draw it with 4 vertices. And yours may look different from mine or from your neighbors because it just depends on where you put those vertices. I'm just going to kind of do it kind of where they're at. And if you want to label those, you can. That might make it a little bit easier to talk about. So I'm just going to call this North Shore, South Shore, the West Island, and the East Island. So those would be my 4 vertices. And then I'm going to come in and draw my edges, which are my bridges. And I like to check these off as I do them. So I'm noticing that there is this bridge that goes from the North Shore to the West Island. So I would need an edge there. I'm also noticing that there's another bridge that does the same thing, that goes from the North Shore to the West Island. So I'm actually going to need 2 edges, which means so that I can see both of those, I will curve at least one of those. And you don't have to necessarily curve both. You just want to make sure that you can see them both. So that would take care of those 2. I'm also noticing 2 more bridges that go from the West Island to the South Shore. So I would do the same thing there. I have 2 edges, so if you want to curve one or both of those. And then since I'm on the West Island, from the West Island, I'm only noticing 1 more bridge, and that is connecting the 2 islands. I'll need an edge there. And then I have this bridge connects north to east, and this one east to south. And that's all of my bridges. So I kind of wrote over them or checked them off as I can. So this is my graph that I've made for this Königsberg Bridge problem. So when it asks us to figure out here if we can travel each bridge exactly once, what it's really asking is it possible to have an Euler path? An Euler path, so I just remember E for Euler, E for edges. Euler paths basically mean that you want to travel each edge exactly once and no more than once. So what we can do is we can use Euler's theorem to figure this out. We started recording, right?
Yeah.
All right, so using Euler's theorem, I'm actually going to find the degree of each vertex. I usually like to list this in parentheses. So if I count the number of edges coming out of each vertex, I can see that N has 3 edges. or is degree 3. E is also 3. S is also 3. And then if I count the edges here on W, it looks like I've got 1, 2, 3, 4, 5 edges there. Oh, didn't mean to erase all that. Let me put it back.
Hit undo. There you go.
Perfect. So this one is 5. So Euler's theorem tells us that if you have all even, if every single one of your vertices has an even degree, then that means that an Euler circuit is possible. If you have exactly 2 that are odd, that's an Euler path. And if you have any more than 2 that are odd, then that means an Euler path or Euler circuit is not possible. So on this one, the famous Königsberg bridge problem, it is not possible. So there is no Euler path or Euler circuit. There's no way to travel each bridge exactly once without having to retrace your steps and travel a bridge more than once. So no Euler path or Euler circuit. And again, the reason for that is because I have more than 2 odd vertices. If I have any more than 2, then it's not possible. Any questions on that example? Questions about similar problems? All right, so we're kind of going to do the same thing with this next example. So this one is a layout. This one actually shows a floor plan for an office. So we're going to start again by drawing our graph. And then we're going to use that graph to determine if an Euler circuit or an Euler path is possible or neither. So on this one, it's a floor plan for an office. On floor plan problems, you want to make sure that each of your locations is your vertex. And then each of the ways that you travel between locations would be your edges. So in this case, my locations, the places I'm trying to get to would be the rooms. So that means that each room will be a vertex. And then how do you travel from room to room? You go through doors. So that would make the doors my edges. So I'm going to start just by putting each location here. So I'm going to have, let's see, 1, 2, 3, 4, 5, 6, 7 vertices. Again, yours might look slightly different just because it depends on where you put them. I'm kind of trying to put them where they are on the picture. And some of these will actually have doorways to the outside. This one being an office building, there is no doorway to the outside. But if it does, you would have to include the outside as a separate location. All right, so that's just each of my rooms or my locations. So those would be my vertices. And then each doorway is how I travel from vertex to vertex. So I'm just going to check these off as I go through them. So like I'm noticing that there is a door that goes from A to G. So I'll draw an edge there. There's another door from A to B. So that's an edge. I can see like I've got A completely done. There's no other doors there. So if you want to maybe check that off or cross it out or something, you can always do that. I just might go alphabetically here just to be a little bit systematic about it. So B, I've already got the doorway from B to A, but there's going to be another door that goes from B to E. I just like checking these off just to make sure I don't miss any. There's 2 doors going from room B to room C. So again, I'm going to curve at least one of those. I can see both of them. And then there's 2 doors. So B's done. I'm going to go to C. There's 2 more doors that go from C to D. That takes care of those 2. So I've done all the doors from C. From D, I've got 2 doors that go to E. And then D is complete. E, there's still a door there that goes from E to F. And there's a door from F to G. And I'll just double check, and I think I've included all of my doors here. So this would be my graph for this floor plan. All right, so now I'm going to go through Euler's theorem again. I'm going to find the degree of each vertex and use that to determine if an Euler circuit, an Euler path, or neither is possible. So A has a degree of 2, B has a degree of 4, C has a degree of 4, D has a degree of 4, E's degree is 4, F is 2, and G is 2. So if I look at these, I notice that they are all even. And so if they're all even, that means that an Euler circuit is possible. All right, so the instructions here said to draw a graph, we did that. Use it to find either an Euler circuit or path starting at vertex A. So we know an Euler circuit is possible because all the vertices are even. So now we just need to find one. And this is where your answer will again differ from mine or from someone else's because it just depends on what order you travel. It does specify that it wants us to start at A. So we will go ahead and start there. So from A, we could probably go, we've got a few choices. We could go to either B or G. I'll go ahead and I'll go to G. So you can do wiggly edges here to kind of track where you're going. Another thing you can do is you can also number to show which order you're going in, or you can just list them. So I'm kind of doing both here, numbering my edges as I travel them and listing the order that I travel each vertex. You can do just one or the other of those, as long as you have a way to specify your order. Now I'm at G. So from G, I really have no choice since I've already traveled that first edge. The only place to go now would be F. So that's going to be the second edge that I travel. And I would list F next. From F, since I've already traveled into F, the only way that I can travel is out, which goes to E. So that's edge number 3. And then now that I'm at E, I actually have quite a few choices. So I could go to D, I could go to B. I think I'm just going to go ahead and go to D. And when I do that here, I can do that with either of these edges that go to D. So I might just do this outside one, but you may pick differently. That's okay. And then from D, I can go to C. I could go back to E. I might go ahead and do that. I might go back to E. But you've got lots of choices here. All right, so that's my 5th edge. So now I'm back at E and I have no choice now. I've traveled all the edges out of E except for this one. So that means I'm going to B next. So that would be edge number 6 now. Now I'm at B. And so at this point, I could go to either A or to C. But in this particular instance, I don't want to go to A yet, right? So there's lots of correct answers here, but that doesn't mean that you can just go anywhere. So I do eventually want to get back to A because I am going to make an Euler circuit. But if I went back to A right now, I would miss the edges down at the bottom. So that means I have no choice then but to go to C. And it doesn't matter which one of those, I'll just do the inside. So I'm going to do that one to go to C. So that's number 7 now. So now I'm at C. So I can either go back up to B or to D, but if you look at this, if I went back up to B right now, then I would miss the edges at the bottom. So I really have no choice but to go to D. That's going to be number 8. And then now that I'm at D again, I have no choice but to go back to C. That's edge number 9. And then now that I'm at C, the only thing left out of C is to go back to B. That's edge number 10. And then my last edge would go from B to A. So it looks kind of crazy when we're done sometimes, but that's okay. And again, you may have a different answer than what I got or what someone else would get. It just depends on what order you decided to travel them in. Any questions?
That one, you have to travel every single step in the path.
You have to travel every single edge, right? So E for Euler, E for edges, right? So if it says Euler, then we know we have to travel every edge exactly once and no more than once, and we can't miss any, right?
Great. Thank you.
All right, so we'll go ahead and move on to the next one. This one, we've got like a street map. So same idea here. We're going to use this. In this case, it's a practical scenario here. Use this to draw a graph and then figure out an Euler circuit or path. So this is a mail carrier problem. The mail carrier needs to drive through the neighborhood below, driving only on streets with mailboxes. So if a street has mailboxes on both sides, the mail carrier will need to travel down the street twice to get both sides. So no mail carrier is going to go like to the mailbox on one side of the road and then to the mailbox on the other side and then go across again, across again. What they're going to do is they're going to drive up one side, or if they're walking, walk up one side, and then later walk back down the other to deliver mail. So we're going to draw a graph representing the streets that the mail carrier must travel and then use it to find an Euler circuit or Euler path through the neighborhood. So that makes sense. We don't want them to travel any edges they don't have to. We don't want them to waste time driving down streets that don't have mailboxes. And we also don't want them to have to drive back down a street that they already delivered to if we don't have to, right? So it makes sense that we would try to get an Euler circuit or an Euler path at least out of this. So when you have your street map problems, this one's a little bit different. Usually your vertices are the locations and then your edges are how you get from location to location. With street maps, your vertices are the intersections, right? So anywhere that you see an intersection on your streets, that is going to be where you put a vertex. And I would include the outsides with that as well, because I mean, technically there's probably a street that runs up here. It's not showing us that. So we would definitely need to outside intersections as well. All right, so those are my vertices, but if you look at these, I may not need all of these. Now, if we were traveling every single street, then I think we would need to travel, every edge, and we would eventually come to these vertices. But if you look, some of these I have no reason to travel to. I actually think there's maybe just one of them that I don't need to include, and that's this one. I don't need that one because there's no mailboxes connecting to that. So I'm gonna exclude that one when I draw my graph. So I kind of drew this over it, but I'm gonna redraw, right? So just kind of over here, I'm gonna try and put them basically in the same places. And I'm just gonna redraw my graph over here on the right. All right, so it looks like I've got what, 11 vertices, and then my streets are my edges. But again, in this one, I don't need to travel a street that doesn't have mailboxes. So I'm only going to draw an edge where there are mailboxes on a street. And again, I have some that have mailboxes on both sides of the street. So for example, right here, this street has mailboxes on both sides of the street. So I'm going to need two edges here because the mail carrier is going to travel down one side of the road. And then they're going to travel at some point later on, they're going to travel the other side of the road to deliver mail on the other side of the street. And I'm going to kind of cross these out or check them off as I get to them. That takes care of those two. I'm just going to kind of go through this. You can do this in any order that you want to. Anywhere that I notice that I have mailboxes on both sides of the street, I'm going to curve my edges a little bit just so I can see both sides of the street there. Just kind of cross these out as I get to them. So like here, I noticed that on this street, there's only mailboxes on one side of the road. So I don't need two edges on that one. I only need one edge. One side of the street that has really like being able to cross these out as I do them. That way I make sure I don't miss any, don't count any twice by accident. This one, again, I just have mailboxes on one side of the street. Just the one edge there. So this is my graph for this one. Yours might look slightly different just depending on where you put your points, but if you put your vertices basically where they were on the map, you should pretty much look like this. All right, so now that we've got our graph, let's mess it up. Let's figure out if we can do an Euler circuit or Euler path by finding the degree. I can see here the degree is 2. These aren't labeled, so it's a little bit harder to talk about them. You could always label them if you really want to. I'm just going to kind of move left to right and list the degree of each vertex here. This one here is an interesting one. Looks like I've got 1, 2, 3, 4, 5, 6, 7, 8 edges coming out of that. Just counting the edges out of each vertex, that's how we're finding the degree here. Any questions on how we found any of these numbers or our graph? Okay. So from here, I'm going to use Euler's theorem. So Euler's theorem says if every single degree is even, then an Euler circuit is possible. An Euler circuit just means that we're traveling every single edge exactly once, and we're able to finish back where we started, right? So if it's an Euler circuit, we will end up where we started. So if they're all even, you have an Euler circuit. If you have exactly 2 that are odd, you have an Euler path. An Euler path is the same idea. You're traveling every edge exactly once, except with an Euler path, you don't get to finish back where you started. And then if you have any more than 2 odd vertices, that's when it's neither, right? So if I look here, I've got a lot of even numbers, but there are 2 odds, right? So I have 2 odd numbers here and here. So since I have exactly 2 that are odd, that means that an Euler path, but not an Euler circuit, is possible. So it should be possible for the mail carrier to drive through this neighborhood and drive down every street with mailboxes exactly once, driving back down the streets that have mailboxes on both sides. They shouldn't ever have to retrace the steps or travel an edge that doesn't have mailboxes. But they won't be able to finish back where they started, right? So when we find our Euler path, you do have to start at one of the odd vertices, and then you'll end at the other one. So it doesn't really matter which one of these 2 with arrows that you pick, but you're going to pick one of those 2, right? So I'm just going to go ahead. I'm going to start on the left. And this one, you can't really list the letters because we don't have letters here. So unless you decided to put letters on these, basically we're just going to have to number our edges as we go through. So I'm going to start at this one that I've highlighted green, this one right here. So I'm going to start there and travel each edge exactly once. So this is going to be edge number 1. From there, I could either go down or to the right, but if I went to the right now, there would be no way for me to get back down that street that goes down. So I actually need to travel down. It doesn't matter whether you go left or the right, but I need to travel down. And there's no choice but to go back up the other side of the street. And then from there, I have no choice but to go to the right. And then from there, I have a few choices, but there is one choice that I don't want to do right now. And the choice that I don't want to do right now is I don't want to go to the right because I know that I have to end at the other odd vertex. So this is the one that I'm going to end at, which means I'm not ready to go there yet. But in terms of where you go from here, you could either go down or up. It doesn't matter at this point. So yours might be different from mine. I'm going to go ahead and just go down. I'll go like this, so that's edge number 5, and then I have no choice but to go back up. And that's gonna be the other side of the street. And then again, I don't wanna go to the right yet because that would not give me a way to get to this upper part of the neighborhood here. So then I'm gonna go up, doesn't matter which side you go up. Just gonna do that one. From here, I don't wanna go back down yet, right? I'm basically gonna travel the entire upper part of the neighborhood here before I go back down. So I'm just gonna kind of go counterclockwise is what I'm choosing, but you may choose to do this in a different order. So I'm just gonna kind of go around the edges here, kind of in a counterclockwise way. And finally, go back down the other side of all these streets. Finally, back down.
Just for a minute.
Last one, out of the neighborhood.
Oh, no, that was server, but I'm gonna make it also,
So this would be one possible path.
no, I'm looking you off for him for roasting him so badly.
So this wouldn't be so bad as long as
I'm
as long as they're just driving through, they could basically drive to the next neighborhood that they need to deliver to. So I think this is okay that they're not ending back where they started. Any questions? All right, so what we're gonna look at next is a coloring problem with maps. All right, so this one in particular is a map of Kentucky's congressional districts. And so this is 6 districts in Kentucky. They've got them labeled over here on the left-hand side to let you know which color is which district. So they're using 6 different colors. And I think that makes sense here just because they're trying to let you know which one is which. But if we were drawing this on a map, we really don't necessarily need to use 6 different colors. Typically, when we are coloring a map, we'd like to use the fewest number of colors possible. And really all we want to do is we just want to make sure that none of the districts or states or countries or whatever we're looking at, none of them that border each other should be the same color. So like if you have one that's orange, it shouldn't be bordering one that's also orange, right? So the first thing we're going to do here is we're going to draw our graph of this map. So on the map problems, when you have countries or states or counties or districts or whatever you're looking at, again, your locations are your vertices, right? So each district in this case is going to be a vertex. So I'm actually going to have 6 different vertices, and I'm going to roughly kind of put them where they are. So this red one was District 1. The orange one was kind of over here. That's District 2. The yellow one. Here's District 3. District 4 was my green one. This purple kind of color is District 6, and then the blue one, District 5. All right, so those are going to be my 6 districts or my 6 vertices, and I just kind of roughly put them basically where they are, right? Roughly where they are in the graph. So yours might look slightly different just depending on like where you put those points. And then our edges are going to be how we get from district to district. Well, how do you get from one district to another if you cross a border, right? So everywhere that we have a border is going to be an edge. So for example, I'm going to start with one, and typically this is a good way to do it when you draw your graph. Start with one on the edge. I would not start with one that has a lot of bordering districts. I would start with one that doesn't border a lot of districts. So like maybe District 1. I'm noticing that District 1 does border District 2, right? So like this border between the red and the orange districts. So I would draw edge then from District 1 to District 2. And then the red district, District 1, it also borders the blue district, which is District 5. So I'm also going to draw one there from 1 to 5. Might move my 2 there just to get it out of the way so I can do that and put my 2 back in. You can always curve your edge too, that works. All right, so that takes care of all of the bordering states to District 1, bordering districts. So I might go ahead and just put a check mark there to say, hey, I'm done with District 1, and then move on. Again, I think this is easiest if you start with ones that don't have a lot of bordering districts. There may not be a lot of those. District 3 isn't bad. So District 3 borders District 4. So I could draw an edge there. District 3 also borders the orange district, which is District 2. So there's an edge there. And then I think that takes care of our little yellow Louisville district there. So that one's good. The orange one, I've already got a lot of those. So I've already got District 2 with both 1 and 3. But if you look, that orange district, it actually borders every district, right? So I don't yet have one from District 2 to District 4, the orange to the green. So I'm gonna do that one. And then District 2 to District 5. Orange and blue, where they bordering each other there. And then purple and orange, District 2 and District 6. That takes care of the orange District 2, the one that borders every other one. And I can check real quick and just kind of look, and sure enough, I've got an edge that goes directly from 2 to every other vertex. All right, so then let's see, my blue district, District 5, I've already got it going to District 1, but it also borders our purple District 6. So there should be an edge from 5 to 6. And the blue and the green, District 4 and District 5 border each other. And again, you can curve that, or I might just put my little number 6 so that it's out of my way. I think that takes care of District 5. I don't see any other borders there that I haven't included. And then I'm just going to go ahead and do the green district, District 4. So the only one I haven't got yet is the purple. So District 6. There should be an edge that goes from 4 to 6. That takes care of District 4. And by the time you get to the last one, guys, so these can definitely be a little bit involved, but like by the time you get to the last one, it should already be done, right? So you should have gotten it with all the other ones. And sure enough, if I look at that purple district that I saved for last, I've already kind of highlighted all the borders there. So I've got all my edges drawn. All right, so this is my graph, and this is what I'm going to use to color my graph. Any questions at this point? Okay, so this is where we're going to start coloring, right? So when we color this, remember, we are wanting to use the fewest number of colors possible, right? So we don't want to have to use all 6 colors that they do unless we absolutely have to. And we kind of do this the opposite way. Instead of starting with the districts or states or countries that have the fewest number of borders, it's good to start with the ones that have the most, right? So I would start, in this case, remember that the orange district bordered every single other district, right? District 2 bordered every other one. So I would start with that one, and you can pick whatever color you want. I might just pick blue. I like blue. So District 2, I'm going to color that one blue. And if you have colors, you can do it that way, or you can just put a B next to it, or write the word blue, or even just, you know, put color 1 and color 2 and color 3. Right? I'm going to go ahead and color this. So I've colored that one blue. So then I would move on to another one that has a lot of borders. So I can just look at my graph to kind of get an idea of this. So like looking at my graph, like I can see that there's only 2 edges coming out of 1. There's only 2 edges coming out of 3. I would probably wait on those. I would pick one that has more like District 4, District 5, right? District 4 has 4 edges coming out of it. District 5 also has 4 edges coming out of it. So I would maybe pick one of those to do next. All right, so I'm just gonna go ahead and pick 4. And so the idea is I want to use as few colors as possible. So the question is, can I use the same color? Can I use blue for District 4, right? And so as long as it doesn't border another district that also uses blue, then I could go ahead and do that. Unfortunately, 4 does border District 2. So I can't use blue, which means I'm gonna have to pick another color. I'm just gonna pick red. You can pick any color you like. So I'm gonna go ahead and make District 4 red. All right, and then I'm gonna move on to another one. So another one that we said that had a lot was District 5. So that one's got 4 edges coming out of it. Can I make 5 blue? So it borders District 2, which means I can't. Can I make it red? I want to use as few as possible. I can't use red either, right? It borders both District 2 and District 4. So unfortunately, I can't use blue and I can't use red. So I'm going to have to go ahead and use the third color. So I'm going to just pick green, and you pick whatever color you like. All right, so I made 5 green, and then where do I go next? Again, you want to pick ones with lots of edges, lots of edges, right? So since 1 and 3 only have 2 edges and 6 has 3 edges coming out of it, I'm going to go ahead and pick 6 next. So if I can, I don't want to have to use the fourth color, right? So can I use blue? Nope. 6 borders or connects directly to 2, right? Can I use red? Nope. 6 has an edge directly in District 4, which is red. Can I use green? No, I can't, right? So it's also bordering District 5. So you want to check all of those though before you introduce a new color. So I'm going to go ahead and introduce purple. So I'm going to make District 6 purple. All right, so hopefully we can get away with this in 4 or fewer. So let's move on then. So either 1 or 3 at this point is fine. So let's just go ahead and do 1. Can I make 1 blue? No, I can't. It borders District 2. Can I make red? Yeah, I could do red. So District 1 does not border District 4, so red would be okay. Purple would have also been okay here, right? So it doesn't really matter which one you pick. Green would not work though, right? So District 1 borders District 5, so I can't use either blue or green. I'm just going to go ahead and use red. Again, purple would have been also okay. And then moving on to District 3, I can't use blue and I can't use red because it's bordering District 2 and District 4. But I could use either green or purple, right? Either of those would be fine. I'm just going to go ahead and use green. That's fine. So now I've got all of them colored. So now if I were to actually color my graph with these new colors, so District 1 would now be red. Kind of was before too, but District 4 would also be red, and you'll notice, hey, they're both red, but they don't border each other, so that's okay, right? District 2 would be blue. It's the only blue one, and that makes sense because it bordered every other district, right? So if any other one were blue, it would kind of clash with that one. And then District 3 and District 5 are both green, but that works just fine because they don't border each other. There's 3 and 5. And then District 6 is purple. And that's just fine because it's purple. So in my final coloring, I managed to do it in 4 colors. So the fewest number of colors that are necessary is what's called your chromatic number. So in this case, my chromatic number is 4. I could have done it in 4 colors in this particular example. Any questions? I can answer. So we're going to move on then to Hamilton side of things. So this is where we kind of switch gears, right? So when we are looking at traveling our edges exactly once, that's Euler, right? E for Euler, E for edges. But there are certain examples where I actually don't want to travel my edges. I want to travel my vertices, right? So the traveling salesperson problem, that is a classic example of a Hamilton circuit or Hamilton path, where I want to travel each vertex exactly once. And I don't want to have to revisit a vertex. So this is definitely switching gears. It doesn't matter here if you travel every edge or not. Matter of fact, you won't typically travel every edge. So in this one, it says a risk manager of a company must give presentations this week over new safety protocols at each of the company's offices in Scranton, Philadelphia, Pittsburgh, and Erie. So he will give the first presentation in Scranton on Monday, then travel to each of the other cities, visiting a different office each day, and then returning to Scranton on Friday. So he would like to plan his trip efficiently in order to cut down on driving time and spend as much time as possible at each office branch. So the driving times in minutes between each of these cities is shown in the table. And so we're going to start by just drawing a complete weighted graph representing this scenario. All right, so yours may look a little different because it just depends on where you put your cities, right? So I'm just going to go ahead and I'm going to kind of do this in 4 corners. And I'm going to put some abbreviations here, but since I've got both Pittsburgh and Philadelphia, I've got PH and PI there. So this is just how I'm deciding to do it. Yours might look different. Like if you did yours in like a triangle with one in the center, yours is going to look a little different than the way mine's going to look. I just decided to do mine in kind of a rectangle shape. And then this is going to be a complete graph, which means we're going to draw edges from every vertex to every other vertex. And we're going to label those edges with the number of, in this case, the number of minutes it takes to drive from one to the other. So from Erie to Scranton, how many minutes does that take? It says in the table that takes 311 minutes. So I'm going to label that with the weight of 311. So this is going to be a complete weighted graph, and then I'm going to draw edges to every pair of vertices, and I'm going to weight them with numbers. And you'll notice that numbers in there twice. From Scranton to Erie is the same thing from Erie to Scranton. Right? So then let's see, Erie to Pittsburgh. Doesn't matter what order you do this in. So from Erie to Pittsburgh is 119 minutes. I'm just going to go ahead and do the outsides first. So Pittsburgh to Philadelphia is 279. You notice that there's some blanks in my table. That's just because like it's 0 miles or 0 minutes from Pittsburgh to Pittsburgh, right? Or from Philadelphia to Philadelphia. Scranton to Philadelphia is 118. And then I'm going to need Pittsburgh to Scranton. That one is 283. And Erie to Philadelphia is 386. I got them all here. All right, so that's my complete weighted graph. All right, so we just want to make sure that this person is able to travel from Scranton on Monday to every other city exactly once, and we want to do this as efficiently as possible, right? So we want to basically use this information to see, okay, what would be the way that would take the least number of minutes, right? Should we do Scranton to Pittsburgh to Philadelphia, Scranton to Erie to Pittsburgh to Philadelphia? So this one on part B, it says to find the number of possible Hamilton circuits in the complete graphs that you drew and list each starting and ending in Scranton. So you're actually going to go through, this is basically the brute force method, which is we're going to list out every single possibility and then compare them all to find this is the best, right? So this is where I would just list them all out. But before I list them, let's find the number of possibles. So we're going to use this formula n-1 factorial. We're going to use that to find the total number of possible Hamilton circuits that we're going to see. So n is the number of vertices. In this case, there's 4 cities. So I have 4 vertices. So I would use the formula here. This would be 4 minus 1 factorial, 3 factorial. And then you can use the factorial button. So on the TI-30XIIS calculator, you're going to type in the number 3, and then you're going to go to PRV, and then arrow over to factorial, right? So that's on the TI-30XIIS. I know I don't have that on this screen, but you would type in the number 3, then click the PRV, which stands for probability, that button. And then the third one over, if you arrow over to it, is factorial. On this one, I'm going to need to find it. See if I can find a factorial. There we go. It's the 4th one. All right, so this is 3 factorial, which is the same thing as 3 times 2 times 1. So this would be 6. I hope you guys can see that. You see the 6 on the calculator? Barely. If I pull it over, I don't think that helped any. There, I just kind of pulled it over there for a minute. You can see the 6. All right, so there's going to be 6 distinct circuits here, starting and ending at Scranton. So I'm just going to start listing these out. So for example, one of them might be if I just went around this thing like clockwise, so Scranton to Philadelphia to Pittsburgh to Erie and then back to Scranton. That would be one possibility. If I went counterclockwise, then that would be Scranton to Erie to Pittsburgh to Philadelphia and then back to Scranton. So that's 2 of them. But actually, if you look at this, they're really the same thing, right? Like if I went from Scranton to Philadelphia to Pittsburgh to Erie to Scranton, that's the same thing just in reverse as if I went Scranton, Erie, Pittsburgh, Philadelphia, Scranton, right? So even though it says that there's going to be 6 distinct circuits here, Hamilton circuits, technically half of those are just going to be repeats, right? So like technically this one is just a repeat of this one. So it's really the same thing there. All right, but then I still have some more to find. So those are the same. Let's see, we're always going to start at Scranton. We could do Scranton to Erie. And then I don't want it to be the same as what I've already got. So I already did Scranton, Erie, Pittsburgh, Philadelphia. So how about Scranton, Erie, Philadelphia, Pittsburgh, and then back to Scranton. So that would be another one. And then I know that another one would just be the same thing, but in reverse order. So if I just reverse the order of those, that would give me another one. Like the same. These 2 are the same. These 2 are the same. And then let's see. What have I not got yet? So I've done Scranton, Erie, and Scranton, Philadelphia. I haven't done Scranton, Pittsburgh. Let's see, Scranton, Pittsburgh. I don't want to do the same one I've already done. And I already did Scranton to Pittsburgh to Philly. So how about Scranton to Pittsburgh to Erie, to Philadelphia to Scranton? I don't believe I've got that one yet. And then that is the same as if I did the reverse order. Scranton, Philly, Pittsburgh, sorry, Scranton, Philly, Erie, Pittsburgh. Back. So there's my 6 different Hamilton circuits. And so now part C, I'm gonna find an optimal route for the manager using the brute force method and then list its total weight. So I'm basically just gonna try each one of these and see which one is best, right? See which one is the fewest number of minutes. The nice thing is though, is that there's only 6 and I don't need to try 3 of them because 3 of them are the same, right? So I'm basically just gonna try, let's just try these 3. And I know that they're the same as these, so I don't need to try that second set there. All right, so let me go through these one. So this first one is Scranton to Philadelphia, which is 118. Then Philadelphia to Pittsburgh, which is 279. And then to Erie, which is 119. And then back to Scranton, which is 311. $118 plus 279 plus 119 plus 311. So if you can see on my calculator there, I've got 827. That one would be a total of 827 minutes. So then let's try the next one. So this next one is Scranton, Erie, Philadelphia, Pittsburgh, Scranton. So that's going to be Scranton to Erie is 311. Then to Philadelphia, which is 386. Then to Pittsburgh, which is 279. And then back to Scranton, which is 283. Would be that route. 311 plus 386. 279 plus 283. My guess is that one's not going to be the best. I'm getting 1,259 on that one. So yeah, definitely not the best one. All right, and then one more here. So then the last one there is Scranton, Pittsburgh, Erie, Philadelphia, Scranton. So from Scranton to Pittsburgh is the 283. And to Erie is 119. And then to Philadelphia, 386. And then to Scranton is the 118. That was 283 plus 119 plus 386 plus 118. And I'm getting 906 for that one. All right, so these are all the possibilities here. I don't need to worry about this set because those are just the same thing in reverse order, right? So I don't need to worry about those. So which one of these is the best? Well, the one that's the fewest number of minutes. So the first one here would actually be the best answer. So this would be the most efficient way to travel to all 4 cities would be to do Scranton, then Philly, then Pittsburgh, then Erie, then back to Scranton. Or the reverse of that would be the same thing, right? And that would be a total of 827 minutes. Any questions here? So this is the brute force method. This is the best method in terms of you're going to find an optimal solution, but it gets really crazy to have to do this for all the possibilities if you have any more than 4 vertices. So this is about our limit. If we have any more than this, it gets very, very tedious. So what we're going to look at next are not optimal solutions, but these are approximate optimal solutions. They don't guarantee to find us the absolute best answer. They just guarantee that we'll find a good answer, right? Which is good enough because they're a lot less tedious than absolutely trying every single possibility and then figuring out which one is best. All right, so these 2 methods are the nearest neighbor algorithm and the cheapest link algorithm. Again, these are for Hamilton circuits, right? So this is not where I have to travel all the edges, right? That's Euler. Hamilton's means I just need to travel to every vertex. So like on this graph, I need to make sure that I travel to vertex A, B, C, D, and E in some order, right? And I don't have to travel every single edge. But I also don't want to retrace my steps. I don't want to have to go back to C or go back to D a second time, and I don't want to miss any. I will do a Hamilton circuit. So the rule for Hamilton is you don't want to travel to any vertex more than once, except to go back to where we started, right? So in this case, it says starting at vertex A. So I will travel to A twice just because I want to go back there when I'm done, right? Same thing as with the last problem. Like it makes sense if you're traveling, you would like to go back home when you're done, right? So the nearest neighbor algorithm, you do need to pay attention to where you are starting. So they're telling us here that we're starting at vertex A, and it is what it sounds like. You're going to pick your nearest neighbor. So right now we're at A, and we're going to travel to whoever is our nearest neighbor. So if I look at all the edges that are coming out of A, I've got 46, 50, 51, and 37. Right? So which one of those would I pick? I would pick whichever one is nearest, or basically whichever number is smallest. In this case, that's going to be 37, right? So I'm going to include that edge here. So this is just how I choose to show my work. It's just to say I'm going to include that edge. Which means if I was at A and now I've traveled that edge that's labeled 37, now I'm at B. So now I'm going to do the same thing. I'm going to keep traveling to the nearest neighbor. I'm going to keep looking at who's the closest to me, or basically which number from where I'm at is the shortest. And that's the one I'm going to choose. But there are 2 problems that you can run into, and those are you cannot create a circuit, right? You can create one once you're done, right? But you should not create a circuit until you've traveled to every single vertex. So I don't want any circuits along the way. And then you should never have 3 edges coming out of the same vertex. So no more than 2 edges coming out of the same vertex. So if I look at from B, obviously I'm not going to travel 37 again. So my choices are 48, 41, and 44. And so my nearest neighbor in this case would be the 41. So can I include that one? Sure, I can. That one's just fine. It doesn't create a circuit. It doesn't create 3 edges out of the same vertex. So I'm going to include that edge, which means now I'm at vertex D. So let's do this again. So from vertex D, my choices are 53, 50, or 28. And so which one of those do I want? Well, 28 would be the nearest. So can I include that one? Yes, I can. That one's just fine. It doesn't create a circuit. It doesn't create 3 edges out of the same vertex. So now I'm at vertex C. as I've included the 28. All right, so now from vertex C, I'm going to look at what are my choices. So from C, I could do 44, 51, or 33. And so the best choice there would be the 33. Can I include that one? Yes, I can. All right, so that one works. And so now I'm at E. And at this point, you might notice that I've basically traveled to every vertex exactly once. So this one seems to work out good. All I need to do is just close my loose edges. So if you notice that, you realize that, hey, my loose ends here are A and E, because they only have one edge coming out of them. So if you notice that, you could just skip ahead and say, hey, that's what I'm going to do. I'm going to travel to 46. If you don't notice that, you just keep doing the same thing. So right now I'm at E. My choices are 46 and 48. Which one would I choose? I would choose 46. Sure enough, that one is fine. It does create a circuit, but that's okay because it's the whole circuit here. So I'm going to ask to just pause for a moment and take a break here for a second. I did like an updated version of this. Yeah. All right, so we're going to try another example of the nearest neighbor algorithm with the same graph, but some different numbers. And we'll look at this one and do the nearest neighbor, and we should run into some instances where we'll actually run into those three edges or circuits on this one. All right, so we're going to start again at A. And so this time my nearest neighbor would be 1. And typically you're not going to run into any issues with your first two edges. So typically we'll always be able to include those first two numbers. So I can include 1, and then from B, my choices are 7, 6, or 5. So 5 will be next smallest. So I can include that one. Now I'm at C. And then from C, my choices are 2, 9, or 8. And so 2 would be the smallest there. But 2 runs into an issue. So if I were to include 2, that makes a circuit before I've traveled to every single vertex. So I would not want to include 2. So I'm going to not use a wiggly edge there, get rid of that. And if you want to cross it out, you can, just to kind of keep track of, hey, I'm not going to use that one. So I'm still at C then. So from C, my choices that I have left are 8 or 9. And so 8 would be the smaller of the two. So I'm going to choose 8. And can I include that one? Sure, I can. That one's good. It doesn't make a circuit, and it doesn't create more than 2 edges out of the same vertex. So I can include 8, which means I've now traveled from A to B to C to D. And then we can keep going through this. So I'll keep looking for the nearest neighbor. However, you may notice at this point that I've traveled to every single vertex except for vertex E. So if you happen to notice that, you know that's the only choice here, right? So basically what I'm going to do next is travel to vertex E, which is going to be the 10, right? But if you don't notice that, that's okay. You just keep going through the same process. So technically my choices from D would be 10 or 3 or 6. And so technically the smallest of those would be 3. But then can I include that? No, I can't, because that makes a circuit, right? And it's a circuit that doesn't include every vertex. So I can't include 3, which means next smallest would be 6. Same issue there. It closes a circuit. It also creates 3 edges out of vertex B, and you can't do that. So, and I wouldn't use 6. And so then you're down to the only one left, which is 10. So whether you notice it or not, you'll get the same thing. Eventually we would travel to 10. So now I'm at E. And then same thing here. If you notice that you've traveled to every vertex, you can just close up your loose edges. If you don't notice it, then you just keep going, right? So the next one would be 4. That's the next smallest, and sure enough, that's fine. So it makes a circuit, but it includes every single vertex. So that is my answer. That is my complete circuit here. So I would include the 4. So on this one, it just ended up going all the way around the edges of the graph. That just happened to be what it is. What is my Hamilton circuit? Well, we traveled from A to B to C to D to E, and then back to A. So we traveled to each vertex exactly once. We didn't ever retrace our steps. The only vertex we went to more than once was the starting vertex, just so we could make a complete circuit. And then to find the total weight here, I'm just going to add up all the ones that were included, right? So 1, 5, 8, 10, and 4. Which would be 28. So my total weight here is 28. If they give you units, include that. It could be money, it could be number of gallons of gas, it could be number of miles or number of minutes. In this one, they didn't give us any units. Any questions here on nearest neighbor algorithm? All right, so then we have one more algorithm for Hamilton circuits, and that is the cheapest link. And so this is the same one, the same graph. We're still going to start at vertex A. But we kind of have to switch gears here. We're kind of switching our thinking. When we did nearest neighbor, we were starting at A, and we were kind of traveling our graph as we went along. With cheapest link, we're not going to do that. So yes, it does tell us to start at vertex A, but I'm not going to worry about that until I get my answer at the end. All I'm doing here with cheapest link is I'm literally looking for the cheapest link. I'm looking for the smallest number on the entire graph, right? And these don't have to connect at first, they'll connect in the end. So I'm just going to look for what's the absolute smallest number anywhere on this graph. I'm noticing that I do have a 1, so that would be the smallest number that I'm seeing. And if you want to, you could actually just go ahead and list all of the numbers and then decide whether you're going to include or exclude them. I like that because I tend to miss some. So for me, like, this helps. So I'm going to kind of just put like a few little marks here next to these just to make sure I get them all. And like, if I just list these in orders, I've got the numbers 1, 2, 3, 4, 5, 6, 7, 8, a 9, and a 10. So I just like to start by listing them least to greatest. This is not how I would do nearest neighbor though, right? So can I include 1? Yes, I can. Typically, I can always include the first 2. So I can also include 2. And in this case, they happen to be connected, but even if they weren't, that's okay. They don't have to connect right now, as long as they connect at the end. All right, so then can I include 3? So the same restrictions apply. You can include it as long as you don't create a circuit or create 3 edges out of the same vertex. Right now, if I were to include 3, that would give me 3 edges coming out of vertex A. So I cannot include that edge. So what about 4? Yeah, I have the same issue with 4, right? So if I included that one, again, that would give me 3 edges out of vertex A, and I can't have that. So I have to exclude 4. Can I include 5? So I have an issue there as well, right? I can't make a circuit unless I've traveled to every single vertex, and 5 would make a circuit, so I can't include that one. What about 6? That one's maybe a little bit tricky, because if we highlight it, it almost looks like there's a circuit, but that's not really a circuit. Even though they look like they intersect, there's not a vertex there, right? So it's kind of like an overpass on the highway, right? One's going over the other. They're not actually intersecting. So this is okay. We can include the 6. We basically right now, like there's a path that goes DBAC or CABD, same thing. So that one's okay. What about the 7? Can I include the 7? Yeah, so that one doesn't work. If I included 7, that would give me 3 edges out of vertex B. So I can't do that one. Does 8 work? That's maybe another tricky one. So if I included 8 right now, that would make a circuit, and I've not been to every vertex. I still haven't been to vertex E. So the circuit here would go like A, B, D, C, and then back to A. So yeah, that one's a little bit tricky again, but that would not work. I can't include 8 because it would make a circuit. What about 9? Yeah, 9 would work. So we can include 9. So it doesn't make a circuit. It doesn't have 3 edges out of any one vertex. At this point, you may notice that we've been to every vertex. So all I need to do is close up my loose ends. So my loose ends would be whichever vertices only have 1 edge coming out of them. But if you didn't notice that, you just keep going. Can I include 10? Yes, I can. It does make a circuit, but it's the answer, right? That would complete my circuit here because I've been to every vertex. So I would include 10. So I didn't really worry about the fact that they said to start at vertex A. Now, when I list my answer, that's when I would worry about that. So starting at vertex A, if you travel kind of in a clockwise direction, we went to B. And then from there, we went to D. From there, we would go to E. From there, we went to C. And then from there, back to A. But if you went in like a counterclockwise direction, you could have listed this as A, then C, then E, then D, then B, and then back to A, which is the same answer, just in reverse. So you don't need to list both, but either of those would be correct. And then again, to find our weight, we just add up which ones did we include. So we included 1, 2, 6, 9, and 10. You'll notice that this is a different answer from the nearest neighbor algorithm. Sometimes you get the same answer. Sometimes it's different. Sometimes nearest neighbor is better. Sometimes cheapest link is better. Neither one is guaranteed to be optimal. They're just guaranteed to be good solutions. So on this one, we happen to get, even though it's a different answer, we happen to get the same weight. So either one would be just as efficient in this case. So 28 miles or 28 minutes or $28 or whatever those units might be. Any questions on nearest neighbor or cheapest link? All right, so the last examples that I have ready for us here are on trees. So this is just asking us to list the 4 properties of trees and then use them to decide which of these graphs are considered trees or not. So you do want to make sure you know the properties. So in order to be a tree, your graph has to be connected. Your graph cannot have any circuits. in a tree, every edge is a bridge. Meaning that a bridge is an edge that if you remove it would disconnect your graph, right? So that means that in a tree, every single edge, if you took it out, would make it disconnected. And then you should have, if you have n vertices, there should be n-1 edges, or another way of saying that is however many vertices you should have exactly one fewer edge. So we can use these 4 properties of trees to figure out if our graphs here are trees. So if we look at the first one, first of all, it is connected. I don't have like 2 separate parts. There is a way for from every point to get to every other point. So it is connected. There aren't any circuits. I'm not saying like where you would travel like in a loop or travel 2 different ways to get to the same point. Every edge is a bridge. What I would encourage you to do with that is just to kind of cross out or cover up each edge one at a time and see if that would disconnect your graph. So on this one, if I got rid of that edge from A to D, then all of a sudden that makes point A separate from the rest of this graph, right? So it would disconnect A from my graph. And then do that one at a time. So I could check that for each edge. So like if I go to this one, if I remove that, yeah, it would disconnect B from the rest of my graph. What about if I remove this one? That would actually create a disconnected graph because I would have this part disconnected from this part, right? So that one works as well. So you just check them one by one. And sure enough here, that's the case. So every edge on this one is a bridge. If I took it out, it would disconnect one part of my graph from the other. And then let's check the vertices and the edges. So I have 1, 2, 3, 4, 5, 6, 7 vertices. So that means that I should have 6 edges. And so 1, 2, 3, 4, 5, 6. So sure enough, this one works. This is a tree. Any questions on that first one? All right, so on the second one, is there anything we noticed that works or doesn't work here?
Got a circuit.
Yeah, it's got a circuit. So as soon as you find something here that doesn't work, you can just say, hey, this is not a tree. You don't necessarily have to check the rest of the properties here. So in order to be a tree, all 4 properties have to be met. So like, just because one of them is met doesn't make it a tree, right? Just because you've got 7 vertices and 6 edges doesn't guarantee that it's a tree. But if it meets all 4 of those, then it would. So in this case, we could say it's not a tree simply because it has a circuit, which I've highlighted there. I think it's also true that you could say here that the reason it's not a tree is because every edge is not a bridge. So you could also do that as an explanation. So like, for example, if I removed this edge, my graph is still connected, right? There's still a way to get from every vertex to every other vertex. So you could also maybe use that as an explanation. Also, you could count up. So I've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. So if it were a tree, if it has 8 vertices, it would have 1 fewer. It would have 7 edges. But if I count here, I've got 1, 2, 3, 4, 5, 6, 7, 8 edges. So the fact that I don't have exactly 7 edges would also make it not a tree. And actually, I could make this one into a tree if I removed not just any edge, but for example, if I removed this edge, if that were gone, then it would be a tree. Anything we notice on that last one? It's not connected. That's usually an easy one to spot. So it's not a tree because it is disconnected. So just the fact that this part of my graph is separate from this part is what would do it here. Also on this one, we have 1, 2, 3, 4, 5, 6, 7, 8 vertices. But we have 1, 2, 3, 4, 5, 6 edges. So there would have to be exactly 1 fewer for it to work for a tree. So I could probably make it a tree if I added an edge, right? Like if I added 1 here, then that would do it. Any questions I can answer on trees? All right, so then the last example I have prepared is to use Kruskal's algorithm to find a minimum spanning tree and its total weight for this weighted graph that we're given. So we have another weighted graph here. And so there's a lot of numbers going on here, but basically they've just used numbers to label each vertex instead of letters. So they're just calling this is vertex 0, this is vertex 1, vertex 2, 3, 4, and so on. And then the numbers on the edges are representing the weights. So Kruskal's algorithm, it's basically the cheapest link algorithm. You're basically just going to choose the smallest number that you possibly can, and then choose the next smallest and the next smallest. What's different then between the cheapest link and Kruskal's algorithm is that it's okay to have 3 edges out of the same vertex, right? So circuits are not okay in trees, as we saw, right? If it's a tree, you can have no circuits, but it is okay if you have 3 or more edges out of the same vertex. So we're basically gonna go through this like we would with the cheapest link algorithm, except we can't include an edge if it would make a circuit, right? As long as it doesn't make a circuit though, we're good. So I'm just gonna kind of do these one at a time, starting with the smallest number. I'm noticing that there's a 1 there. So I could definitely include that edge. So there's my 1. I think I'm going to use a different color since this is kind of already red, just to make it a little easier to see there. My next smallest number, I'm seeing a 2, and actually I have more than 1 2. So could I include this 2? Yeah, that's fine. I can include that. I know that they're disconnected right now, but that's okay. They'll be connected in the end when I'm done. Can I include the other 2? Yeah, no issues there either, right? So as long as you don't make a circuit, you can pretty much use it. Let's see, do I have any 3s? I don't see any 3s. Do I have any 4s? I do. Is this one okay? That one's just fine, yeah. So I can include that 4. What about the other 4? Is that one okay? Yeah, that one's good too. So I'm just gonna keep doing this. The question is, when should I stop? So how do I know when I'm finished with this? One thing you could say is, well, I know I have to go to every vertex, right? So that could be one thing that you're looking for, but I wouldn't maybe just use that, because what if you accidentally went to it more than you should have, right? What I would do here is I would use that last property we talked about. We said, however many vertices it has, it should have 1 fewer edge. So if I count these, right, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. Which means if it's going to be a tree when I'm done, it should have 1 fewer edge. So that means it should have 8 edges when I'm done, because we're making a minimum spanning tree, right? So basically what I'm going to do is I'm just going to keep including these until I've included 8, right? Since I know that this should have 8 edges. So that's how I'm going to keep track of, like, how do I know when I'm done? So let's see, so far I've included 5 edges, 1, 2, 2, 4, and 4. So let's see, do I have any 5s? Not seeing any 5s. I have a 6. Is it okay to include the 6? Oh, yeah, so that's where we run into an issue, right? So you basically, the only issue you have to look out for is no circuits, right? We said if it's a tree, you can't have circuits. So if I included 6, that would have made a circuit. There would have been a circuit right here, right? If I had included 6, so I can't include that. All right, so let's not include 6.
I got some doors today.
Got all of these. What about, let's see, I have a 7. Is this 7 okay? No, that makes a circuit again. Yes, that one I don't want to include. Is this 7 okay? Yeah, that one's fine. Yeah, so I could definitely include that one. Sorry, I switched to the bigger font here. Any more 7s? I don't see any more. Let's go to 8s. So this one, okay. Yeah, that one would be okay. Is this one okay? No, yeah, so that one would make it into space, right? And I don't want that. Matter of fact, on this one, you could have picked either of the 8s. So you just can't pick both of them. So if you had decided to pick this one first, that would be perfectly fine, right? But the problem is then if you picked this one, then it makes a circuit. So there's possibly several correct answers here. So on this one, we are going to include 8, but only one of them and not the other, right? Because if I include both of them, it makes a circuit. All right, so I'm just going to stick with that one at the top, and then I'm going to cross that one out because that would make a circuit. Let's see, I've included 1, 2, 3, 4, 5, 6, 7 edges so far. So I only need 8. So I only need one more. 9 is my next smallest number. Is that one okay? It is. And so that's it. I'm done, right? And if I look at what I have here, I should have a minimum spanning tree. I should have a tree that travels to each and every vertex exactly once, that is connected, that doesn't have any circuits, right? That meets all the properties that I had for trees. If you want to redraw it just to make it a little bit easier to see, you can. The good examples of this are things like electrical lines or fiber optic cables or water pipes, right? Move it up a little bit.
There it is.
Yes. So like, as long as there's a way for like the electrical current to get from every point to every other point, or for the water to get from every place to every other place, then it's fine. So this would be my example. And then I just add these up to find my total weight. So 1 plus 2 plus 2 plus 4 plus 4 plus 7 plus 8 plus 9. All the ones I included there. And in this case, I get 37. Any questions that I can answer on this problem or any other problem or another question that we have? Thank you guys for your time. Good luck on your exam 4.